Hello class, this is a video tutorial on further trig identities and equations. In this video we'll be looking at t-formula. For harder trig equations, it is sometimes easier to treat the problem as a regular algebraic equation. So if we apply our double cosine angle identity here, we would eventually get to this point. So that should also be equal to 0. But then from here, it might be more beneficial if we let u equal cos x, which will make this expression become 2u squared. This expression becomes negative u, and negative 1 stays as negative 1. And then from this point, you can solve as a quadratic. In this method, I factorize using grouping. You could use quadratic formula or whatever method that you would like. And only at the end, you would re-substitute in the cosine x at the end and solve using trig from that point. But for the bulk of the problem, quadratic equation solving methods have been used. So from here all the way up into here, we're using quadratic solving methods. In this way, the problem has become simplified. Now, by using the tan double angle identity, we can learn the t-formula and apply them, which is exactly what we're going to be doing for this. We're going to be changing these into simpler algebraic equations and only having to deal with the trig portion of it only at the end. So first, we need to learn the t-formula. So here we go. So we start with the double angle identity of tan. First, we need to get it to become tan of theta. Well, if we let a equal theta on 2, what will happen there is tan 2 times theta on 2. That will cancel, but a is now going to be 2 tan theta on 2 all over 1 minus tan squared theta on 2. This can just simplify as tan theta, which is what we wanted. Now this doesn't look as neat just yet, but if you give it a moment, and we'll say that let t equal tan theta on 2. So this will give us now theta on 2. The left hand side is still tan theta. Theta on 2 is now t all over 1 minus tan squared theta on 2 is now going to be t squared. Now, it may not be very obvious, but this here, if we go back all the way to basics, that's going to be opposite over, not hypotenuse, over adjacent. Which, if we apply it just like that, in our triangle here, if we say we let that be theta, opposite is 2t, adjacent is 1 minus t squared. We can find sine and cos by finding the hypotenuse. So h squared is equal to 2t whole squared plus 1 minus t squared all squared. Expanding this, we get 4t squared plus, this is going to be outside of 1, so squaring the first, squaring the last, double the product of the middle, so minus 2t squared. Collecting like terms, 2t squared minus 2t squared, well, that's going to be 2t squared plus 1 plus t to the power of 4. I'm just going to quickly rearrange this just to make it a little bit more obvious for the next step that I'm about to do. That leaves us with t to the power of 4 plus 2t squared plus 1. Now it may not seem like it, but this here is actually a perfect square. It's t squared plus 1 all squared. That's h squared. Now to find h, we take the square root of both sides, which leaves us with, well, if we square root this, that leaves us with t squared plus 1. So h is t squared plus 1. Well, from there, if we do sine of theta is 2t over t squared plus 1. Cosine of theta is 1 minus t squared over t squared plus 1. I just remembered, whoops. I'm going to rearrange this one last time and you'll see why in a moment. I'm going to make it 1 plus t squared. You'll see why in a moment. And that there is our trig identities using the t formula. So if we begin with t equals tan theta on 2, we can get these three identities here. By using these, it'll make our trig equations a little bit more simple as we move forward. So if you can start memorizing these, I'll demonstrate to you how we can apply them to these sorts of equations. Okay, hope to see you then. Best of luck.